My name's Nick Braithwaite. I'm currently the Executive Dean of the STEM faculty, and I'm here to welcome you all this evening. But before I go any further, I have to tell you that we haven't planned any fire alarms, so if it does go off, we should leave quickly in an orderly fashion, either through there or through there, and assemble where everybody else is assembling. Well, it's no good to be telling you where it is because it's disorienting going out of here. You'd be pointing in the wrong directions. Okay, now we have some people joining us online. We're live streaming this, so welcome to those people in particular. And let me say also that because of that, if we're asking questions afterwards, we've got some roving mics, and if we can let the mics get to the people before they ask the questions, then those online will be able to hear it. We'll do what we can to keep those online engaged as if they were in the room. We're also going to be using Padlet to allow people to engage during these lectures and to provide feedback at the end if necessary. There is a QR code that I'm told works extremely well from the front row. If you're further back, then there's bit.ly/OpenStem, and that should connect you there as well. Okay, now, what have we got? We've got a series of lectures, and this is the first one. They're called OpenStem Talks. This is the first one on this, a very special and auspicious day for the Open University, because it is now 50 years since our charter was delivered to us. So the first 50 have gone down okay. Our mission now is to get the next 50 started, and that's what we're doing with this series of talks. We're going to cover a whole range of STEM in these talks. Some will be lectures, some, as we got tonight, 2 lectures. Some might be a debate, and some may include some demonstrations. I certainly hope those will be occurring, and OU STEM YouTube channel will be the place to watch them. We also have Facebook presence as well. Now tonight, let's get down to tonight. We've got 2 speakers. The first one is Professor Andrew Holland, who's going to talk about the Clockwork universe.
Wrong Andrew, Nick.
Andrew Holland. Did I say Andrew Holland? Right, can we just cut and start again? That's terrible. Will you forgive me? He won't even forgive me. We do this a lot. And now, tonight, we have 2 incredible lecturers, far better than what you might have heard just now. We have Professor Andrew Norton. The other thing is, I'm reading this too, who's going to talk us about something which Andrew Holland knows nothing about. Andrew knows about the Clockwork universe, adventures in time domain astrophysics, and that's what I know. I've known of Andrew all the time that I've known these last 20 years or so. That's his speciality. He started, as the other speaker did, at the University of Leicester. They got their PhDs from there at any rate. And I've just discovered that the second speaker taught the first speaker how to use a telescope back in those days. And then sometime later, the first speaker taught the second speaker how to use a telescope when they were here. So they've been exchanging views on things astronomical for some time. Anyway, where is Andrew now? Well, after he postdoced at Southampton, he came here. He's now risen to the dizzy heights of Professor of Astrophysics Education, and he's led the presentation of quite a lot of modules in physics, astronomy, space, science modules. He's been involved with 2 in the undergraduate and the postgraduate curriculum. His research focuses on the time domain astrophysics that he's going to tell us about, and compact interacting binaries and wide field photometric surveys. Now, Andrew has also been a vice president of the Royal Astronomical Society, and he's extremely well connected. There is something called an Erdos-Bacon Sabbath number, which shows your connectivity to mathematicians, actors, and heavy metal rock bands. And you have to have a low score on that to be anybody. Andrew's is 13, which is apparently quite a low score. Well done. Now, he's also written various things like 60 Seconds Adventures in Astronomy. I hope you're going to talk for more than 60 seconds tonight. What else has he done here? Oh, he's interested in Doctor Who and Star Trek. Well, these people are. Let me go on to the second lecturer. Professor Simon Green. Did I get that right, Simon? Yeah, okay, he's the only Simon I know. Near-Earth asteroids, a matter of life and death. That's his topic tonight. Well, he's a professor of planetary and space science in the Open University's School of Physical Sciences, same home as Andrew. I've told you where he got his PhD. He's interested in these small objects out there in the solar system. He's been on missions that have gone to comets. He's worked on missions that have collected stardust. And he's got unpronounceable comets that were visited here in the Rosetta mission. but he's also been to Titan and Saturn with his missions. So he's been around the solar system a bit. So we've got the stuff out there, and we've got the stuff more local. What a night it's going to be. Let's see. I should tell you also this key fact about Simon. Asteroid 9831 is named Simon Green. No space. Simon Green, in recognition of the work that he's done on asteroids and trans-Neptunian objects. Right, I'm going to hand over to Andrew in just a moment. I'd like to thank you for joining us right now. There will be some questions afterwards. If you're here, we can offer you some refreshments afterwards downstairs. If you're online, we'll tell you what they're like. Okay. And I think that's probably enough for me. So let's get Andrew to come and deliver the first talk.
Thank you very much, Nick. Thanks for the introduction, and thanks everyone for coming. It's nice to see so many familiar faces here. So the subtitle of my talk is Adventures in Time Domain Astrophysics. I'm going to take the chance in the next half an hour to tell you about some of my favourite astrophysical objects that I've investigated over the years, and a couple of the time domain astrophysics projects that I've been involved with. So this is my opening question, which is on the Padlet website that Nick mentioned. Does the universe run like a machine? And it's a question for you to consider, if you like, and some little subsidiary questions there on the left about how stars might vary, how they might move, and how we might measure that, which might trigger some things for you to think about, and which hopefully I'll give you answers to as we go along. And some of you may recognise the clock there, which is also at Leicester University. So the foundation of really what I'm going to talk about really goes back to Isaac Newton. 350 years ago, he developed his theory of gravity, and that describes how planets and stars move through space and how things vary in this clockwork manner that I'm going to talk about. He was also one of the first people to use a telescope to observe the night sky, and one of the first people to recognize that you could split white light into its constituent colours into a spectrum using a prism, and all of those aspects will have relevance to what I'm going to be talking about shortly. It's important to really think about, when we talk about a clockwork universe, measuring time, our measurements of time really are rooted in space, in astronomy. After all, as you know, the Earth spins on its axis once every day, the Moon orbits the Earth once every lunar month, and the Earth and Moon together orbit the Sun once every year. And these are then three clocks that are present in our solar system that form the basis of our measurement of time to a large extent. And when we think about stars out there in the galaxy, some of which you can see in the background here of this picture, they too have their own inbuilt clocks. They vary and they move in certain ways, and that's what I'm going to be telling you about. One of the important things to realise about stars, though, again, you can see from this background picture, even to the best telescopes, they generally appear as just a point of light. Now, that's fine, because we can see that these points of light have different brightnesses, and indeed they may vary in brightness with time, and that's the basis of what I'll talk about in the first part of my talk on light curves of stars, how the brightness of stars vary with time. The other thing we notice in a picture like this is that stars have different colours, and that tells us that they emit different spectra. They emit different proportions of light at different wavelengths in their spectrum. And measuring the spectra of stars can actually tell us about how they move through space. And I'll come to that in the fourth and final part of my talk here. In between those two parts, I will tell you about two of the projects that I've been involved with over the years, SuperWasp and Zooniverse, and I'll explain what those are. And I'll give you just a couple of examples of the many variable stars that are amongst my favourites, things that I've studied both in visible light and in X-ray light, and I'll show you those. So let's start then with thinking about light curves and what a light curve is. The simplest measurement we can make in astronomy really is just taking an image of the night sky, and there's one there shown on the left, lots of stars in that. And what we can do if we choose is take a particular star in that image and measure its brightness. We can then take repeated images of that same field, each of which contains that same star, and we can measure the brightness of that star in each of those images, and we can string all those measurements together to make a light curve, and that's what I show on the right there. Each little black dot is a measurement of brightness of that one particular star at a particular time, and at the top there we have a light curve spanning about 8 years, and below that a zoom in to about a month's worth, and below that just a zoom in on a few nights of data. And in that zoom in, I think you can see already that that star is varying in brightness in a fairly characteristic and periodic way. If we want to understand how a star is varying in brightness, we want to see what periods of variation are present in that light curve, and how we do that is shown here. So on the left in red is a light curve. That red trace shows how the brightness of a particular star is varying with time, and we can split that up, deconstruct it if you like, into 3 separate signals shown by those purple traces. They each have a different period of variation, a different frequency. They each have a different amplitude, and if we add those 3 purple traces together, we get back to the red light curve that we started with. But one way of displaying that information in those 3 purple traces is as shown on the right in what we call a power spectrum. This is a plot of amplitude against frequency. So each one of those 3 signals that form the red light curve has its own characteristic frequency, so we get 3 spikes in this power spectrum. And if we look at the data in that representation, we can say, yes, that light curve contains variations at those 3 particular frequencies, those 3 particular periods of variation. And the mathematical process of going between the two we call a Fourier transform. The details of that are not important for now, but the point to take away is that we can analyze any light curve, such as the one in red shown there on the left, into its different components, as shown there on the right. So if I go back to that light curve I showed you just a couple of slides ago, and we take the power spectrum of that, we see that it actually contains 2 distinct signals, a low frequency signal corresponding to a period of 5.1 days, and a higher frequency signal corresponding to a period of 1.8 hours. So whatever this particular star is, this point of light, it contains these 2 clocks, these 2 periods of variation. What we can do is fold that light curve at each of those periods in turn. By folding the light curve, I mean, if you imagine that light curve stretched out on a strip of paper, and you just take a 5.1 hour segment of it, fold that onto the next 5.1 hours, and the next, and so on. So we overlay all those repeated signatures at 5.1 hours, we get something as shown on the left there, and the red line shows the average of all those many, many cycles added together. And that's a very characteristic light curve shape that we recognize as coming from something called an eclipsing binary star, shown in the cartoon at the bottom. In an eclipsing binary, we have a pair of stars orbiting around their common center of mass, and once per orbit, star number 1 passes in front of star number 2, and star number 2 passes in front of star number 1. So we get an eclipse each time, and that's the characteristic shape we see there. Now, if we take that same light curve and fold it now at the shorter period of 1.8 hours, we see this rather different shape, this sawtooth or triangular shape. And this is characteristic of what we recognize as a pulsating star. It's literally a star that's getting bigger and smaller, brighter and fainter, cooler and hotter as it does so every 1.8 hours. And so what that's telling us is this point of light that we've observed the light curve for contains 2 stars as an eclipsing binary, but one of those 2 stars is also a pulsating star. So these 2 clocks, these 2 regular periods of variation, are both present in this same star. Now, that light curve and some others which I'll show you shortly were obtained with this project called SuperWASP, the Wide-Angle Search for Planets. SuperWASP consists of 2 installations, one in La Palma in the Canary Islands, one in South Africa, so that we can see northern and southern hemisphere skies simultaneously. As you can see, it contains 8 of these lenses on a single robotic mount, each of them only about 14 centimeters across, so they're quite small telescopes, but they're very wide angle. So they take images such as the one shown there in the bottom. It's about 15 times the diameter of the full moon. So a typical image might contain 100,000 stars in the one image. And what we did with SuperWASP over the course of a decade or more was just take repeated images of the night sky, minute after minute, hour after hour, night after night, year after year, and we built up billions of data points from this. In fact, we have light curves of 31 million bright stars, and they're all over the sky, apart from the galactic plane, the plane of our Milky Way, where the stars are just too close together to separate with these small telescopes. And the important point about these light curves with SuperWASP is that they have a long baseline over a decade of measurements, as I mentioned, but they also have a high cadence. That means we have multiple observations of each star every night, many per hour in some cases. So the main aim of SuperWASP was to detect transiting exoplanets, planets orbiting other stars that pass in front of the star as seen from our line of sight. And it's been very successful at that. When a planet the size of Jupiter passes in front of a star the size of the Sun, it will block about 1% of the starlight, so causing this characteristic dip in the light curve. And from that you can work out the size of the planet, and from other methods that I'll talk about later, we can also work out the mass of the planet. So SuperWASP has found about 160 of these transiting exoplanets. They're all what we would call hot Jupiters. They're about the size and mass of Jupiter in very close orbits around their star, so they're very hot planets. And the graph on the right there shows those 160 planets with orbital period up the left, ranging from about 1 day to 7 days, and the mass of the planet from half a Jupiter mass to a few Jupiter masses along the horizontal axis. But that's only 160 exoplanets, and I said there were 31 million light curves there. So what I spent a lot of time doing over the last few years was looking through all 31 million of those light curves to see if I could find signals of other variable stars. Now, I wrote programs to do this and ran them on our computing cluster here at the OU. It took 100 years of computing time, but luckily I was able to run this on 50 computers simultaneously, so it only took 2 years of real time. And in those 31 million light curves, I found 1.6 million periodic variations, with periods ranging from about 1 hour to 1 year, shown in that cumulative histogram there on the right. So 1.6 million possible periodic variable stars in this whole data set. And here's just 6 of those 1.6 million folded light curves, and you can see a variety of profiles, a variety of shapes. These correspond to things like pulsating stars, eclipsing binary stars, rotating stars, some of unknown type and some that may just be junk. Each of those light curves that I've done there is plotted over 2 cycles, repeated, just to help you see the variation that's going on. What I've done with those 1.6 million light curves is upload them to this website called Zooniverse. Zooniverse is a citizen science website where volunteers can take part in real science experiments. There's a lot of astronomy experiments on there, but they cover other areas of science too. And in my project that I've created there, SuperWASP Variable Stars, the task for volunteers is just to try and classify these light curves into the various types, pulsating stars, eclipsing binary stars of different types, and so on. So if you'd like to join in, please do go to zooniverse.org, search for SuperWASP Variable Stars. You can follow the little tutorial there and start classifying stars for yourself, and who knows what you might find. So the light curve I showed you to begin with, that was from SuperWASP. This light curve I'm showing you now is probably the favourite amongst all those many millions of light curves with SuperWASP, my favourite object that we've discovered so far. Now, we may find something better yet to come, but this is my favourite so far. It's an unremarkable star, goes by that name, Tycho 3807759. It's just a single point of light in the SuperWASP images. There's its light curve in the middle, 2 years worth of it anyway. When we analyse that light curve to look at what frequencies or periods are present in it, we see 2 sets of signals in the power spectrum. One corresponding to a period of 5.5 hours, and another set, which are all multiples of each other, integer multiples of each other, corresponding to a period of 1.3 days. So there are clearly 2 clocks in this system, a short period one, 5.5 hours, and a longer period one, 1.3 days. When we fold that light curve at those 2 periods in turn, this is what we see. The one on the left is the 5.5 hour period, and this is a very characteristic shape that we recognise as being a contact eclipsing binary star. The 2 stars in this system are so close together, they're distorted into this sort of pear shapes, and as they orbit around each other every 5.5 hours, we get this continuous variation in brightness, up and down, twice per orbit as one star passes in front of the other. It's a very compact system. You can see the size there for the diameter of the Sun by comparison. So it's a very, very compact system. If we fold the same light curve on the longer period, the 1.3 day period, we get this other eclipsing binary light curve, now with very narrow, sharp eclipses, well separated. So this is a detached eclipsing binary star. The two stars are well separated, they're not so distorted, and they just repeatedly pass in front of each other twice per orbit. So what we know so far then is this particular star contains at least 4 stars in 2 eclipsing binaries. As it turned out, this particular object has had another surprise in store for us, which I'll come back to a little bit later in my talk. Now, so far I've just talked about optical, visible light. We can study some stars using other electromagnetic radiation they emit, for instance, X-rays. And I spent a lot of my time, not least when I was at Leicester University, working in the field of X-ray astronomy, including using some data from this particular satellite, ROSAT, the joint German-British Röntgen satellite X-ray observatory. And this is now an X-ray light curve of a particular star called TX Columbi. So what we're plotting here in this graph is just the brightness in X-rays of that particular star over the course of about 1 day or so. If we analyse that light curve, we see quite a complex pattern of periods or frequencies in there, but the 2 dominant signals are at 5.7 hours and 32 minutes. Now what this object is what we call a magnetic cataclysmic variable star, and this very nice little animation shows what we think might be going on. We have 2 stars very close to each other, a red dwarf star, something much cooler, fainter and smaller than the Sun, which is distorted into this pear shape by a very dense object called a white dwarf, shown in blue there. The white dwarf is the remnant of a star that was initially maybe a few times the mass of the Sun, but has shed its outer layers and collapsed down to be something about the mass of the Sun or less, but the size of the Earth. So it's very dense, has a very strong gravitational field, so strong it's able to pull material off its companion, and we call this an accretion process, as that material gets channeled from the red dwarf down to the white dwarf. The material starts to spiral round the white dwarf and forms this structure we call an accretion disk, but because of the strong magnetic field, it truncates the inner edge of that accretion disk, material attaches to the magnetic field lines, and then channels down to the north and south poles of the white dwarf. And as it hits the white dwarf, it speeds up, gets very fast, gets very hot, and that's where the X-rays are emitted. So as you might have guessed, the 32-minute period that we see is actually the time it takes the white dwarf to spin on its axis. It spins every 32 minutes, presenting a different aspect of this accretion flow to us, and so we see that variation in the X-rays every 32 minutes. The 5.7 hour period is simply the time it takes the 2 stars to orbit around each other. So that's a cartoon of how we think it may look. Here are the results of some other work that I did a few years ago, where we build a simulation of the system inside the computer. So inside the computer we build a computer program that contains knowledge about the equations that control the gravity, the equations that control the magnetic forces in the system. We release packets of gas from the end of the red dwarf star there and see how they flow under the influence of those forces and see how they end up on the white dwarf. And the 4 animations shown here then, they're all for the same orbital period, the same period that the 2 stars orbit around each other, but in each one, the spin period of the white dwarf is different and the magnetic field strength of the white dwarf is also different. And you can see we get different types of accretion flow, ranging from quite puffed up accretion disks to very diffuse disks to a more stream-like flow, or something that's rather ring-like with material channeling onto the field lines from there. So with these sorts of simulations, we can try and understand how these things evolve with time, how they behave, and what the physical properties of the systems are. The final thing I want to talk about, having talked about just brightness measurements so far, is to think about spectra of stars. Now, going back to visible light to begin with, we know that with a prism we can split white light up into its component colours, colours of the rainbow. If we look at the spectrum of a star, we might see something like the image at the top there. We see the band of colours, but superimposed on it are these dark bands in the spectrum. They're what we call absorption lines, and they're due to absorption of particular wavelengths of light by certain elements, certain atoms in the outer, cooler layers of a star's atmosphere. If we convert that coloured representation of the spectrum into a graph, we might get something as shown on the left. This is 3 segments of the spectrum ranging from the violet part of the spectrum at a wavelength of about 4,000 angstroms through the blue into the green at a wavelength of about 5,000 angstroms. And in that graph then each dip in the graph is an absorption line corresponding to a particular element, a particular atom in the outer part of the star's atmosphere. And I'll come back to the spectrum of this particular star in a moment when I've shown you how these are useful. The reason spectra are useful for us, one of the reasons they're useful for us, is because of the Doppler effect. Now, the Doppler effect will be familiar to most of you, I'm sure, in the context of sound. We know that as a vehicle is coming towards us, the sound waves get bunched up in front, and so our ears perceive a higher frequency of noise coming from the vehicle as it approaches. As the vehicle recedes, so the sound waves get stretched out behind it, and our ears perceive that as a lower frequency of sound. Well, we get just the same thing with light. So in the system shown there, the yellow and blue, imagine that's 2 stars orbiting around their common centre of mass, seen from above, and then at the bottom seen from the side. So at some points in the orbit, that yellow star, say, is moving towards us, and at some points it's moving away. When it's moving towards us, the light waves it emits get squashed up, and so any features in the spectrum get shifted towards shorter wavelength, towards the blue part of the spectrum. As that star moves away from us, so the light waves get stretched out, and any features in the spectrum get shifted to longer wavelengths towards the red part of the spectrum. So as shown in the bottom bit of the animation there, you can see those spectral lines alternately moving to the blue and the red. This is the one equation I'm going to show you in the talk, the Doppler shift equation, which just tells us that the shift in wavelength, delta lambda, divided by the original wavelength lambda, is equal to the speed at which the star is moving, divided by c, the speed of light. Now we know the speed of light, we know the original wavelength of the lines, we can measure the shift in the wavelength, so we can work out the speed at which that star is moving. And we can then plot a graph of speed against time, which is shown in the top right part of the animation. And we call this a radial velocity curve. So it's a curve of the radial velocity, the velocity of the star away from and towards us as a function of time. So just from measuring the spectrum, we can then tell how fast that star is moving towards or away from us. So if I go back to that double eclipsing binary star I mentioned a while ago, we went and took spectra of that. Now with a bigger telescope, we could see clearly that this was not one point source, but 2 point sources. That's fine, we thought. That's the 2 eclipsing binaries we were expecting to see. And when we looked at the detailed spectrum of one of them, the 5.5 hour binary, we saw 2 sets of spectral lines moving backwards and forwards every 5.5 hours. So we're able to plot that upper radial velocity curve for those 2 stars. When we looked at the spectrum of the other pair of stars, as we thought, there were 3 sets of spectral lines there, 2 of which moved back and forwards every 1.3 days, but the 3rd set of spectral lines, shown in green on that bottom graph, stayed pretty much constant. So here we've got a triple star. 2 of them are orbiting around each other every 1.3 days, and presumably that eclipsing binary and the 3rd star are orbiting around each other with a much slower period, perhaps a few years, too long for us to measure in this short duration of observations. So this object, which initially to SuperWASP appeared as a single point of light, is actually 5 stars. It's a doubly eclipsing hierarchical quintuple star system containing a close eclipsing binary and a triple star, where the triple star itself includes another detached eclipsing binary. And from the radial velocity curves that we measured and the variations in brightness as well, we're able to work out things like the masses and the sizes of each individual star, how far apart they are, how long they take to go around each other, and so on. And as I say, that's probably my favourite of all the objects that we've found so far amongst the SuperWASP 31 million. The final object I want to tell you about goes back to X-ray astronomy, and this is another class of objects that I worked on for a number of years, so-called accreting X-ray pulsars. This particular object is called Vela X1. It consists of a neutron star accreting from the wind of a supergiant star. Now, what are they? A neutron star is the collapsed core of a very massive star. Something that was initially maybe 20 times or more the mass of the Sun has undergone a supernova explosion, shed most of its material, and the core of that star has collapsed down to become this rapidly rotating neutron star. It's maybe the mass of the Sun, or even twice that, but it has a size of only 10 kilometers across, so it's immensely condensed, very, very dense indeed. And it's orbiting this supergiant star, something much more massive, much more luminous, much hotter than the Sun. And the two go round each other every 9 days or so. The supergiant star has a strong stellar wind, emitting lots of material into space, which the neutron star is able to sweep up as it orbits. And by a mechanism that's still not completely understood, having swept up that material, the neutron star then emits these beams of high-energy radiation from its poles, shown as this sort of lighthouse beam effect. So as it spins on its axis, so this beam of X-rays sweeps across our line of sight twice for every spin of the neutron star. So as shown on the left there, this is now a plot of the X-ray emission over the course of the spin of the neutron star, and every 283 seconds we get a double burst of X-rays as first one beam and then the other beam sweeps across our line of sight. So we can understand this system again using the Doppler effect, or versions of it. If you look at those bursts of X-rays coming from the neutron star, as the neutron star is coming towards us in its 9-day orbit, so those bursts of X-rays appear to arrive at a slightly quicker rate. And as the neutron star moves away from us, so those bursts of X-rays appear to arrive at a slightly slower rate. We can measure a sort of time delay, a time advance and a time delay as the neutron star goes around its orbit. And that's what's shown in the left-hand panel there. And from that variation, we can work out the speed at which the neutron star is moving in its orbit. It turns out to be about 280 kilometers per second. Now, they weren't my measurements, but what we did is shown on the right. We took visible light, optical spectra of the supergiant star. We measured it over the course of 3 weeks, actually, 21 nights, and we measured the spectrum night after night, again and again, and we measured the Doppler shift of the spectral lines from that supergiant star. And when we plotted those on this 9-day period, this is what we found. It showed us that the supergiant star was moving in its orbit at about 23 kilometers per second. Now, combining those two speeds, the speed of the neutron star with the speed of the supergiant star, plus a few other bits of information we had about the orientation of the orbit and things like that, we were able to weigh the two stars in that system and able to figure out that the neutron star has a mass of 2.3 times the mass of the Sun, and the supergiant star actually has a mass of 28 times the mass of the Sun. So using spectroscopy, we were able to weigh the two stars in that system. So everything I've talked about then has been about variability in the sky, variability of stars. And this field of astronomy, I think, has a bright future. I'll just show you one example now of something that's coming online in a few years' time. This is called the Large Synoptic Survey Telescope. It's being built in Chile on a mountaintop there, and it will become operational in just a few years' time. It will observe all the sky all the time. It's quite a big boast, but that's essentially what it will do. Like SuperWASP did, really, but remember, SuperWASP had lenses that were just 14 centimeters across. This telescope has a mirror that's 8 meters across. So not only will it do very wide field astronomy, doing images of very large patches of the sky, it will also be able to see very faint objects, much, much fainter, millions of times fainter than was able to be seen by SuperWASP, for instance. And it will just repeatedly image the night sky again and again, night after night, for many years. The plan is that it will image the entire sky twice a week, each through 6 or 7 different filters, different parts of the visible spectrum. It will discover many, many periodically variable stars, I'm sure. It will also discover many transient objects, things that flare up and disappear night after night. So watch this space, as they say, for news of the LSST. So my almost final slide then is to return to the question I asked you at the start: does the universe run like a machine? I I suspect I hope I've convinced you that to some aspect, indeed, it generally does. I've shown you that various stars, white dwarfs, neutron stars, regular stars, all spin on their axes with periods some as short as a few seconds, some much slower, up to months or more. Pairs of stars orbit each other, again, some with periods as short as a few minutes up to much longer periods, as long as you like, really. And actually, stars can exist in hierarchical multiple systems, combining binaries and triples up to any number of stars, really. All stars really have a variable brightness as well. At some level, all stars are variable. It just depends whether we can measure that level of brightness variability with the size of telescope that we have. And I've shown you that the movement of stars can also be revealed, not least by the Doppler shifts in their spectra. So that's a few of the highlights of things I've worked on over the past few decades. I hope you've enjoyed hearing about them. I'd just like to put up that slide to acknowledge assistance and help I've had from many people over the years, not just here at the OU, but former postdocs who've worked with me and postgraduate students and collaborators elsewhere, one or two of whom are in the audience, I know. So thank you very much.